So in this case, we would like to use the Euler's method to solve this differential equation with the given initial condition on the interval 0, 2. Okay. So again, the equation that we have to handle is this equation, and then let me make the axes. So in this case, notice the following, that we don't really know what the actual points are. We know a starting point, and then we simply have what? Say this is 1. I'm just taking our units here. Okay, so and here is another unit. Okay, and this will be 0.5. All right, so let me label the points quickly. So what we have is that in this case, pardon me, I should have had it ready for you beforehand, but anyways, here we go, and here we go, and then we have 0.5 as our initial value, the initial value problem that we are going to look at. Now, how are we going to proceed here? So we know starting point is 0 and 0.5. Now we don't have the actual coordinates of point, rather we have the direction in which we are moving. So what we will do is, exactly as we use the linearization in calculus 1, we will start here, use this as slope of a small line segment, and see where that takes us. And then what will happen is that we'll take as tiny segments as possible, and we will assume that this rate of change remains effective throughout our domain of interest, and point the values, and graph the points obtained by the values, and that will give us the solution. That will give us an approximate solution. Okay, so once again, what we are going to do is we're going to start here, and we shall take just tiny segments, or see, this is our t-axis here. Okay, so since we have this as our t, so we will take small segments of t and proceed in that manner. So let me just show you calculations. So here, so we had to take a small segment. So assume that we are taking our small segments as, so here we have our delta t, let's take that as 0.25, and then when we get to automation of this by a computer program, we will take tinier segments. Okay, so here we got 0.25, and then where are we starting? Our starting point is 0.5, and then from here we are going to proceed to, what's our next point? 0 plus 0.25, that is, we'll have 0.25, but we have to determine the y coordinate for this one. Okay, because we have to, so for that we are going to use this slope. And how would we do that? Well, we will take the present altitude, then from here we are running by how much? A quarter of a unit, right? And then our slope is how much? And slope will be determined by the point where we started. So this is what? 0.5 square, and this would be what? Simply 0, right? So our y coordinate will be 0.5625. So here what we did was that we went to 0.5625. So this was our first point, and this is the second one. Then we are going to proceed the same way. Okay, and what we are going to do now is that we shall add 0.25 to this, which is our increment. So that will be 0.25 plus 0.25 is 0.5, and then we are going to repeat the process. Okay, that is, take this altitude and then add what? Add our run times. Now this time what will happen? These values will change. Why? Because now we are starting at this point. So let me change this here. Okay, and the x coordinate is how much? 0.25. So from there we went to what? 0.3125, and this is the way we are proceeding here. Okay, so 0.3125. all right. Okay, so let's see where it takes us. So now I'm back at my whiteboard. Okay, so here is this point right here. Okay, and then for this one what I would do is that let's look at this point. Okay, all right, so this would be what? The next point would be, if we go for 0.25 and then 0.5625, that will be approximately here. Okay, and then this point, which is 0.5, then 0.3125, we can see this value is coming down. And then what we will do is that we shall go ahead and connect it by a smooth curve once we have all the other points. But of course I'm not going to take too much of your web time on computing everything by hand. So how about we use, say, let's just use Excel here. Now before I use Excel, let's just look at the procedure that we will use. So notice our procedure is following. That is, we have YA equals B. So what will be our next point? And if we are going in the increments of delta t, then what will happen? We will get to the next point by, next point would be A plus what? Delta t, right? And then for the y value, what we shall have? We shall take B plus delta t, right? Times what? F, this value, the slope that we have at what? T plus delta t, right? Okay, isn't that what we just did over here in our calculations, right? 0.5 plus 0.25, which was delta t, and then we just substituted that value in order to get this pair, right? And then for the next one down the line, that is, see, notice this first, that I could abbreviate it as this, that this is the y value at A plus delta t. What is that y value? That y value is this value, and there is a typo in here. I have to write a t, which I just did, right? Okay, good. So now what we have, say the next point that we are going to go to would be what? Y of A plus 2 delta t. Okay, so in here what will happen now, that we will take the previous height, okay, then of course take the increment. Okay, we are going linearly, which will be our run. Okay, and then what we will do, we will multiply it by the slope, and notice the slope will be computed at what? The slope will be computed at the previous point, right? Am I clear? Okay, so let's proceed like inductively here. That is, say we are going to the kth step. Okay, all right, then what will happen is we will look at this here as the one step before. Okay, and everywhere this one step before will show up. Okay, right here, and that's what our formula will be, the Euler's formula that we are using. And of course we should mention that our k is a whole number, okay, that is greater than or equal to 1, okay, and we will just need as many whole numbers as needed for the subdivision. All right. So now instead of working on those calculations by hand, now let's use Excel. So we are starting with the starting point, then we are giving it the increment, okay, and then what we would do is that we will just go up to 2. That's how far we want it to go, and here we have the starting value 0.5, okay. And for the next one, what I'm going to do is, I know I'm going to take this height plus, what's that, 0.25 is the run that I'm going to use for all of them. And notice that I am typing in the formula here, or that automatically goes in there, okay. And then I'm going to multiply it by the slope, and the slope will be given by what? Y square, let me type that in for you, minus 4 times who? Whatever the t value is. We are going to keep that as a variable here, okay, and here we get the same value, 0.5625. And just bring this cursor here, double click on that, and you can see we got the next one. What was the next value at 0.5? Okay, so either I made a mistake or something went wrong here, because I had 0.1325. So let's go ahead and quickly check, because here it does the same thing. Yes, it computed it at B282. So let's see who made a mistake, I did or the computer did, okay. So let's inspect again. Here I am having disagreement with the computer, okay. So, oh, okay, notice this here. I have no idea what was going on, and you must have caught it, but since I am talking simply to the monitor, okay, we couldn't see it. Computer was correct and I had done a mistyping there, okay. So here we go, okay. So yes, we do have the same values, right? And let's use Excel now. And with Excel, what we will do is say we will go ahead and see how things work with the value when we have the values refined. So let's go ahead and create a scatter plot here. So right here it gives us an approximate solution, all right, and with the increments of 0.25. Now we can repeat the same process with the smaller increments, okay. Say we did this, okay, that is, we go ahead and since now computer is going to work, we'll take much smaller increments, okay. So we start again at 0, and this time we are given going in the increments of 0.01. Let's drag it until we get, oh, just a second, I didn't drag it properly. I should have dragged them together, and we will go as far as up to what? As long as we reach our point 2, all right. So here we go. We went up to 2.01, which is all right, okay. And then what we will do is that here in this case, of course, we have the starting point as 5, and then we are going to go and no, sorry, okay, so we added the y coordinate. Now we will put our run in, right, and now I have to go a little carefully because I made a mistake last time, right, remember that. Okay, so here we will say square the previous y coordinate and then take 4 times the previous t coordinate, right? Okay, all right. Now we should get more, much better approximation in here. Okay, All right, so let's see what we get this time. Okay, we will go ahead and make a graph again. All right, so here the graph of course is similar to the one before, but this should give us a better approximation, and we will see later on that how we have the convergence according to different graphs. Okay, now we are going to use MATLAB instead of Excel. Okay, and we have the same thing, same initial value problem, and let's use MATLAB with delta t equals 0.01, and that means how many segments are we going to go by, and of course there'll be 200 of them, right? Okay, so we'll take like the values of t. Let me take you to MATLAB and explain there. It'll be much better. Okay, so here we have our MATLAB, and the command window, what we will tell it first is that we are going to go with our delta t equals 0.01. Okay, and then once we have that, then our t will be a string of values. How many? We want a range of 200 whole numbers here, right? And I am putting in you can see this here. Yeah, I put semicolon to hold on to it. Okay, and then we have our y as the values evaluated at these points. Okay, all right, and then we will take our starting point for t is 0, and our starting point for y is the initial value that we had, and what we will take in that case 0.5, right? Okay, and then after we take it, then we just simply ask it to do the following, that is for I equals, you could say for k equals, if you wanted we had taken k in the formula, but anyways, so for I equals 1 through 200, what we want t to move in the increments of what? The t at the value, and you can create an M file in this way if you would like. Okay, delta t, so that you can specify your delta t differently every time. And then for y, I plus 1. Okay, now what do we do for that? Remember, we will take the previous y value. Okay, and then we are going to go by delta t, right? Okay, and the delta t will be what? Will be multiplied by, and we have to put a period because we are just going to create that matrix of values, right? Okay, and then we have what we have. We will take the value of the slope, okay, which is what? Which is right here, y square minus 4yt, right? So we will do what? We will take yi, and for before the square we have to put this period because we are not looking at the symbolic values here. Okay, and then what we have to do next is, once we squared it, we will subtract 4 times the previous t value, right? So we have ti, right? Okay, and then we go here. Let's make sure that we have closed all the brackets properly. We'll check it. Okay, all right, looks like we did. So now it's time to end this, right? Okay, and now what I'm going to do is that I'm going to ask it to plot our ty, right? And we will keep the same axis as we had in Excel. Alright, so let me go down to our Excel. The axes were 0 to 2.25 and here -3 to 1, just for a comparison, you know, of what kind of look we got. So we will do this. So we want to plot it and we will give it the axis as that. The axes will be for the x values or t values. Actually we wanted to take it from 0 to 2.5, and for the y values we want it to go from 3 to 1. Okay, and we will say plot, and here we can see the plot. Just a moment. Okay, so here you have the plot, which is pretty similar to what we had in Excel. All right. Okay, so just play with it and use different values and let me know if you have any questions.